Now, we're ready to look at another mathematical relationship, and that is the Arrhenius Equation. The Arrhenius Equation is going to help tie together mathematically temperature and the rate constant K, as well as the activation energy. Okay? This is the Arrhenius Equation. K is the rate constant, of course, okay? And we have the activation energy in there, we have R, we have temperature. So let's talk about each one of these. So that, of course, is our rate constant, our lowercase K. This E sub A, that's the symbol that we use for the activation energy. It is usually put in kilojoules per mole. The R value, we're going to need the one that has units of energy. So if we use the 8.314, that's joules. We make sure we get it to kilojoules, or we put our activation energy into as joules. Whichever is the case, you either work both of them with joules or both of them with kilojoules so that they will cancel appropriately. And that tells me something about temperature. What do you suppose that temperature needs to be in? Well, we see there with the gas constant, it's got Kelvin in there. In order for this equation to work, we better put this temperature into Kelvin. That little e, okay, that's the e on your calculator. It's associated with the natural log. It's the inverse of the natural log, okay? And that leaves us with one last thing, and that is the A, and that is called the frequency factor. And this is another constant, okay? And we won't talk much about it, but it really takes into account various things that we will mention as we get on down the line. But this is really talks about the system itself. What kind of system is it? Solid, liquid, and gas affect the value of that A, and the way the molecules have to be aligned for a collision to be effective comes out from that A. So this is a value that is very specific to the reaction that doesn't change with temperature like the rate constant does. All right, so let's examine this equation. Let's examine it mathematically, okay? We already know that temperature affects the K value. We talked about how it does that in our last lesson. Activation energy will affect the K value. If it's a small mountain that has to get over, reactions take place faster than if it's a big mountain that it has to get over. The rate constant affects the rate because of that E sub A. So let's think about those mathematically. You see that minus sign in there? Now let me go over to the screen so I can point to things. Okay? We've got this little minus sign. When you take E to a negative number, you end up with a fraction. Now if I'm raising it to a bigger and bigger negative number, okay, I'm raising it to a bigger and bigger negative number, then this is going to be a littler and smaller fraction. So K is going to get smaller. Okay? Stop now and take a calculator out and show yourself this. Take e to the negative 5 and then e to the negative 2. Okay? You see how K is affected by bigger E sub A versus smaller E sub A. What we know is that the rate is going to go down as the activation energy goes up. Now, do we know, would we expect that? Let's look at these two different reactions. Okay? If it's got a small activation energy, there's going to be more molecules that can make it over that mountain. If they have more molecules that can make it over that mountain, it is going to be a fast reaction. If the activation energy goes up, that's this guy, a high activation energy, and there's going to be fewer molecules that can go over that mountain. That is going to be a slower reaction. That's when you have little K values. Okay, now let's look at the temperature with this mathematical relationship. Temperature is in the denominator of this fraction. See where temperature is? When temperature goes up, it's in the denominator. What's going to happen to this negative number? It's going to be a smaller and smaller negative number. E to a smaller negative number is going to be a bigger K. Okay, we saw that before. As temperature goes up, the rate goes up, and that's because you got more molecules that can go over the barrier. So as the rates go up, it's the K going up with it. Now we're going to take this equation and we're going to do a little mathematics to it. We're going to take the natural log of both sides of that equation, okay? Because the natural log and then that e, it'll take care of that e term because those are inverse functions of each other. So we have the natural log of k, and we have the natural log of a product, which is the sum of these two things. So we have the natural log of a, the natural log of e to the minus e sub a over rt will make the e sub a, the e, that little e go away, and you're left with what you see there, okay? So that's all that's happened there is I've taken the natural log of both sides. Now what I'm going to do is a little bit of a rearranging because I love linear graphs, okay? And I want to be able to show you that this is a slope-intercept form of a line. What have I done? Well, I've taken that e sub a over rt and put it first, and then did a little regrouping. And then a natural log of a is last. And what I have is the natural log of k and y line up, okay? Negative e sub a over r and little m line up. 1 over t and x line up. And natural log of a and the intercept b line up, okay? So what does all that tell me? Tells me this. A plot of the natural log of k, that's my y-axis, versus 1 over t, that's my x-axis, will give me a slope. Now, which one of those is my slope? What would the slope be equal to? Well, it'd be equal to negative e sub a over r. So if you go in and you do some experiments and you're changing the temperature and you're seeing how that affects the k value, and you do one experiment after another and you collect a bunch of data, you could get a straight line. So we see here a plot of data. What did we plot? You see on the left-hand side over there the natural log of k. That's your y-axis. So I collected some k values. I collected some k values and some temperatures. I did some mathematics to convert those k's to natural log of k's. I did some mathematics to convert my temperatures to 1 over temperatures. I plotted that data here. Okay, and I just put them in an Excel spreadsheet and out popped this graph. I also asked the spreadsheet to give me the mathematical relationship of this line. Y, that was my natural log of k. X was 1 over t. This right here is the natural log of a, which was that frequency factor. And right here is my slope. So we could calculate activation energy based upon that slope. So we're going to do that over here on the whiteboard. We've got a value of the slope equal to a negative 12211, right? That's what I'm reading right off of the graph that this thing gave me. Now the units of that, since it's a change in y, which is no units, over the change in x, and the change in x is Kelvin to the minus 1, the units for this is going to be Kelvin. And that is equal to negative e sub a over r. So if I want to plug in r and put it over here, I have a negative 1221 Kelvin times 8.314 joules per mole Kelvin. Okay, there's my, gosh, it's not showing up very well. Bear with me here while I make this thing write better. There we go. Now, I have that's equal to, I brought my r over, that's equal to negative e. Let's go ahead, e sub a. Let's go ahead and get this minus over here, so that would become positive, and that's e sub a. And we have the Kelvin canceling with the Kelvin, and that would be leaving me with joules per mole. Usually we don't want to leave it with joules per mole, so let's go ahead and move this over a little bit and multiply by divide by 1,000. Okay, and that equals e sub a. And all of that worked out gives me a value of 101.5, and it would be in units of kilojoules per mole. And I will tell you that very typically in the hundreds range is a very typical activation energy for a reaction, so I like that number. The bigger this number gets, the faster the reaction, this is activation energy, right? The bigger this number it gets, usually the smaller the reaction rate, because it's a high mountain it's got to climb. The smaller that mountain is, the faster the reaction is going to be. All right, let's do something else with this equation. There's my Arrhenius equation, and that's the slope-intercept form of it, y equals mx plus b. How many data points does it take to define a straight line? Truly only 2. So we're going to take that equation with 2 data points. We're going to do it for one temperature with one K and another temperature with another K, and we're going to put these equations together, all right? You're just deriving the 2-point equation by writing this equation twice, once with a K1 and a T1. Activation energy would be the same for both reactions, wouldn't it? That doesn't change with temperature. R is not any different, and the frequency factor is not any different. And then we write the whole equation with K2 and T2. We subtract those 2 equations from each other, and you're left with this equation. Now, just a point of clarification on this equation. I have seen this equation written 2 different ways, and students get really thrown off by this because they're wondering which one is right. They're both right, okay? I like this form because K2 minus K1, this is the natural log of K2 minus the natural log of K1, which is what gives me this quotient. And so I have T2 minus T1 in this order. But you will sometimes see that minus in front of the E sub A over R. You'll see that incorporated into the other half, or this other part over here, and all you're done is flip this around. If you take that minus you see on the screen, on the PowerPoint presentation, and you put it inside of here, it just reverses their order. Now for me, 2 minus 1 and 2 minus 1 makes more sense. For me, knowing the Arrhenius equation had a negative E sub A over R in it, I like the negative form. So I like this one better. But if you see this one, you don't say, well, that's wrong. That's not what I learned. It's right also. You just choose which way you want it to go and work with it consistently, whichever you choose. Okay, so now we've got the equation, and I'm going to put it back on the board the way I have it memorized. Okay, I have it memorized like this. Now we have a situation in which the activation energy is given to me. I know this value. Okay, I'm told the rate constant that goes along with 35 degrees Celsius. So let's say I was given K1 and T1, and it wants to know the value of K for 0. So they gave me this temperature, and we're trying to get that. Now, what temperatures do we have to work in? We have to work in Kelvin. So let's go over here and take my 35 degrees Celsius and add 273 to it, and I get 308 Kelvin. Okay, that's one of my temperatures. And I have my 0 degrees Celsius, which is 273 Kelvin. Okay, I have decided to do the one that I know the K for to be T1. So I'm going to call the 35, I'm going to call this one T1, I'm going to call this one T2. Okay, K1 goes with this T1, and I'm going to solve for K2. So the natural log of K2 that I don't know, 1.35 times 10 to the 4, and the unit is seconds to the minus 1. That tells me it's a first order reaction. Whenever I have units of time to the -1, it's a first order reaction. Is equal to a negative E sub A, 102. I'm going to go ahead and convert that to joules, because I have 8.314 joules per mole Kelvin as my R value. So now my joules and my moles are going to cancel. I am going to do T2. T2 is the one that goes with the one I don't know, which was the 0. T2 is 273 Kelvin minus T1, which is 308 Kelvin. Now you'll notice these kelvins are in the denominator. When I subtract it, they're going to be able to cancel with this guy that's in the denominator of the denominator, seems like they're not going to cancel, but they will, okay? And we will be left with a unitless guy, and that should be unitless. Now let's see what I have as far as numbers are concerned. I have, oops, I just advanced to a bunch of stuff there. Let me put this down. I have, not going to change this part, natural log of K2 over 1.35 times 10 to the 4th seconds to the minus 1. And if I put all of this into my calculator, I'm going to get a negative 5.10675. I'm carrying extra sig figs along the way. Okay, so that's what all of this portion equals. Now I've got to get inside of here and get my K2. So I need to get rid of this natural log next. The way I do that is to take the e to both sides, the e of this and the e of this. That's going to get rid of the natural log, and that's going to leave me with K2 over 1.35 times 10 to the 4th seconds to the minus 1, and that is equal to 0.0060557. Okay, this is a unitless number. Still trying to solve for K2, so what do? I multiply both sides by that denominator. So K2 is this value times the 1.35 times 10 to the 4th. Before we plug that in, what should it do? What happened to my temperature? My temperature went from 35 down to 0. I would expect my K, therefore, to have gotten smaller, and the value for K here is 8.18 times 10 to the minus 7, and it will have the same units as this has, okay? So I have a unitless value times this. Now, can we see all those numbers and everything? I don't know. I want to clean it up just a little bit so that when you look up here, it looks better for you, okay? This is times 10, and that's seconds to the minus 1, okay? So now we have 8.18 times 10 minus 7 seconds to the minus 1. And being able to solve for any one of the variables in this Arrhenius equation is something that you should be able to do in this class. All right, what's next? I don't know. Let me find my remote control. Oh, the little word about the frequency factor. That A, which is our frequency factor, it takes into account a few things. One of it is it takes into account the frequency of the collisions. Now, what do I mean by that? If something is in the solid state versus a liquid state versus a gas state. Let's compare gas and liquid first of all. Gas state, the molecules are very, very far apart. In the liquid state, they're very, very close together. You're going to have much more frequency in collisions when you are in the liquid state versus the gas state. So that is played out with how many collisions you're going to have based upon its state. The solid state, now they're really, really close together, but they're not moving past each other. It's hard to make collisions when you're in the solid state. So that is part of that. The other thing that it takes into account is the orientation of the molecules when they collide. If it doesn't matter, okay, that's going to give you a certain value of this frequency factor A. If it does matter, that gives you a different value. So here's an example where if the molecules collided at the top with the red hitting the red, they just bounce off of each other in this example. But if they were turned in such a way that the green could hit the green, then they would react. So not every collision, even if it has a lot of energy, is going to result in a reaction. It has to be oriented a certain way. So those are things that frequency factor A plays out, okay? Don't need to know more about it than that. All right, so what we're going to talk about next, we're down there talking about collision theory, and the Arrhenius equation comes out of that collision theory. We're going to talk about how when a reaction takes place, it's not just all the molecules slamming together that are reactants. There's going to be a stepwise where this has to collide with this, and then this has got to collide with that, and so we have a series of them, and it's not just one big giant, all molecules in the reaction slammed together. So we'll be looking at what's called a reaction mechanism in our next lesson.